Okay, anyway, good morning everybody. Okay, today we shall go with the engineering mechanics where we have come across the term force system. Right. What do you mean by force system? A set of forces which are acting on a body in general we call it a force system. If the line of action of all these forces meet at a single point, we call it as concurrent force system. We call all line of action of the forces meet at a single point. We call it as a concurrent force system. We call it as a concurrent force system. This is what we call as a force system. The line of action of all these forces meet at a point. We call it as a concurrent force system, and this particular point we call it as point of concurrency. That we call it as the point of concurrency. Now, for any structure it could be a stable one. For any structure it could be a stable one. We have come across the various conditions. For a concurrent force system, there are two equilibrium conditions. For any structure to be a stable one, say for a concurrent system, these are the two conditions of equilibrium. Sigma h equal to 0 and sigma b is equal to 0 are the conditions of equilibrium for a concurrent force system. For a concurrent force system, there are two conditions of equilibrium. The net horizontal forces must be equal to 0 and the net vertical forces must be equal to 0. For a non-concurrent force system, how many conditions of equilibrium are? How many conditions? There are three conditions. For a non-concurrent force system, sigma h must be equal to 0, sigma b is equal to 0, and sigma m at any point must be equal to 0 are the conditions for non-concurrent force system. Is that right? Now, we have a set of forces. Okay, we have a set of forces. So this is F1, this is F2, this is F3, and this is some force F4. Okay, now we are required to find out the value of resultant. Whenever the resultant exists, it will mean that that particular system is in equilibrium. Resultant bantu andre, if some value of the resultant exists, if it is equal to 0, then you say it is in a state of equilibrium. If not, if you get some value of r, it is not in a state of equilibrium. That already you have studied, isn't it? Now, for this particular force system, which is inclined at an angle of say theta 1, theta 2, theta 3, and theta 4, etc., we are required to find out the value of the resultant. How we have found out the value of the resultant? Now, resolve each and every force along x direction. Is that right? Now we are going to resolve this particular force along x direction, that is F1 cos theta 1, this is F1 sin theta 1, okay, this one is F2 cos theta 2, this is F2 sin theta 2, okay, this is F3 cos theta 3, F3 sin theta 3, and this is F3 cos theta 4 and F4 sin theta 4. The first thing is, you have to resolve each and every force along two mutually perpendicular directions with the proper sign convention. Isn't it? Now we have resolved each and every force along two mutually perpendicular directions. This is the first step. What is the next step is sum up algebraically all the x components with the proper sign convention. Sum up algebraically all the x components is sigma f of x. All the x components with the proper sign convention. The forces to the right we shall take it as positive, and forces to the left we shall take it as negative with the proper sign convention. Sum up algebraically, that is F1 cos theta 1, then this one is plus F2 cos theta 2, then this one is minus F3 cos theta 3, and this one is minus F4 cos theta 4. We are going to get some value of sigma f of x, say some positive value. Positive value in which direction x component will be acting? To the right or left? Right. Now this x component will be acting towards right. Plus 1 that the x component will be acting towards right. Similarly, sum up all the y components. You are going to get sigma f of y with the proper sign convention. Upward force you are going to take it as positive, and downward force we shall take it as negative. ಇಲ್ಲಿ ಏನು ಮಾಡಿ f1 sin theta 1 plus, here it is minus f2 sin theta 2, here it is minus f3 sin theta 3, and plus f4 sin theta 4. Say you are going to get some positive value. When you get a positive value, in which direction f of y is acting? Upward. This will be acting in the upward direction. Now you can observe that all the these particular set of forces has been reduced to only two forces. We have a number of forces, which is a concurrent system. And finally, it has been reduced to two forces, sigma f of x and sigma f of y. Okay, all forces we are going to get two forces, that is sigma f of x and sigma f of y. Now, this is equivalent to the two forces. Sigma f of x is positive and sigma f of y is also say positive. The number set of forces has been reduced to two forces. Correct? Once these two forces are there, can't you find out the value of the resultant? Yes. By using the Pythagoras theorem, we can find out the value of the resultant. And the corresponding inclination say alpha. What is the resultant of this particular one? R is nothing but equal to root of sigma f of x square plus sigma f of x square. This is the value of the resultant. And the inclination of the resultant is nothing but equal to tan inverse of sigma f of y divided by sigma f of x. This is how we are going to calculate. And you can replace all these forces by a single force which equals the resultant. You will force you can apply this particular force with this inclination. Whatever the effect that is created by these set of forces at this particular point, the same effect will be created by this single force. That replace single force in general we call it as resultant. You have to look ಒಂದೇ ಒಂದು ಫೋರ್ಸು ಇಷ್ಟು ಇಂಕ್ಲಿನೇಷನ್ ಆಗಿದೆ ಈ ಎಲ್ಲ ಫೋರ್ಸು whatever the effect this particular forces are being created, the same effect will be created by the replaced single force. This we call it as resultant. ಕರೆಕ್ಟಾ? ಎಷ್ಟು ಫೋರ್ಸ್ ಇರೋ ಈ ರಿಸಲ್ಟೆಂಟ್ ಇಷ್ಟು ಮ್ಯಾಗ್ನಿಟ್ಯೂಡ್ ಹಾಕಿದ್ರೆ ಈ ಪಾಯಿಂಟರ್ ಹಾಕಿದೆ with that inclination the effect doesn't get altered. Where should that particular resultant should pass? Once again, since it's a concurrent force system, the resultant has to pass through the point of concurrency. That point of concurrency point to pass out. Isn't it? Now, here we are going to get some value of the resultant. Extra value of the resultant. Now, the system is not in equilibrium. You got sigma f of x 0, sigma f of y if you have got 0. What's the value of r? It must be equal to 0. Sigma f of x is 0. Sigma f of y is equal to 0. R is equal to 0. Then the system is in equilibrium. When if the resultant R is equal to 0, when it will be equal to 0? When sigma f of x is equal to 0 and sigma f of y is equal to 0, obviously the value of R must be equal to 0. Then we say that that particular system is in equilibrium. Say here you got some value of the resultant. Now is it in equilibrium now? This system is it in equilibrium? Equilibrium is it now? It is not in equilibrium. Now, since R is not equal to 0, it is not in a state of equilibrium. Now, I want to bring back this system to equilibrium. It is not equilibrium, for which we are going to add a force. We are going to add a force. We are going to add a force. Okay, which is equivalent to the magnitude equal to R. We are going to add a force. What should be the magnitude of this added force? It should be equal to the resultant. Correct? It is acting in the opposite direction, but acting along the same line of action. This added single force, which brings back the system to equilibrium, is what we call it as equilibrium. Equilibrium is nothing but equal to minus of R. If single force add madaka, just add madaka, it should have the same magnitude. It should be acting along the same line of action, but it should be opposite to the direction of the resultant. This single force add madaka, it is to 10 kN. We are going to add a force of 10 kN along the same line of action, but opposite in direction. That added single force here we call it as equilibrium. This force in the add madaka, what's the net value in that particular direction? It will be equal to 0. The system will be equal to 0. This added single force in general we call it as equilibrium. We call it as equilibrium. Now, anyway, when you say a system, concurrent force system is equilibrium, sigma f of x must be equal to 0 and sigma f of y must be equal to 0. Now, to look into that particular, we shall demonstrate that equilibrium condition by using what we call it as a force table. By using what we call it as a force table. In this particular force table, okay, we have various forces, F1, F2, F3 and so on and so forth. We have the various forces. Okay, we have the various forces. Now we are going to get some kind of resultant. When you get resultant, it is not in equilibrium. Then you are going to add one particular force. You are going to add one particular force such that if you add this particular force, it will be in equilibrium. It will be in equilibrium. That we shall see by using this particular force table. Correct? This is what we call it as a force table. Okay. Now you are going to apply this particular force. It has already studied. Whenever you are going to apply a force at the end of this particular string, it passes through the frictionless pulley. Hence, whatever the force you are going to apply at the end of the string, it will be transmitted through this particular string. This is now what it is. Equilibrium of connected bodies. Equilibrium of connected bodies only we have studied this particular one. This is a string which passes through the frictionless pulley. Whatever the load you are going to apply here, the same load will be transmitted to this particular string. Here also, the same load, it will be transmitted to this particular string and this particular string. Now, at this particular point, see, you can observe that all these forces are meeting at this particular point. You have applied some magnitude of these particular forces. You have applied some magnitude of these forces. Is it right? Now, we shall see whether this particular one is in equilibrium or not. Equilibrium alididre, this ring center point correct irta ittu. ಈಗ ನೋಡಿ, if you leave it, it is not just touching. It is not in equilibrium. ಹೌದಾ? ಎಳೆದಾಡ್ತಾ ಇದೆ. Isn't it? It is not in equilibrium. We have applied these particular forces. Okay, and see that. ಇದು ನೋಡಿ, equilibrium ಇರಬೇಕಂದ್ರೆ this would have been at the center. ಈ ಸೆಂಟರ್ಗೆ ಈ ಪಾಯಿಂಟ್ ಇರಬೇಕಾಗಿತ್ತು. So you can see, due to the application of some loading, it has been shifted. Now the system, is it in equilibrium or not? It is not in equilibrium. Now, for this particular string, if you apply that magnitude of the force, then it will be in equilibrium. ಈ ಪೊಸಿಷನ್ ಸೆಂಟರ್ ಪೊಸಿಷನ್ಗೆ ಬರಬೇಕು. ಎಷ್ಟು ಮ್ಯಾಗ್ನಿಟ್ಯೂಡ್ ಆಫ್ ಫೋರ್ಸ್ ಅಪ್ಲೈ ಮಾಡಬೇಕು ಅದನ್ನು ಅಪ್ಲೈ ಮಾಡಿ. You can observe that. Now see, with the application of this particular force, ಈ ರಿಂಗಿಗೆ ಸೆಂಟರ್ ಪಾಯಿಂಟ್ ಬಂತು. Is it right? Now we say that particular system is in equilibrium. ಹೋಗ್ತಾನೆ. ಫಸ್ಟ್ ಹಿಂಗೆ ನೋಡಿ, when ಈ ಲೋಡ್ ಇಲ್ದಾಗ ಶಿಫ್ಟ್ ಆಗಿತ್ತು, ಆ ರಿಂಗಿಗೆ ಸೆಂಟ್ರಿಗೆ ಇರ್ತಿದ್ದ, ಇಟ್ ವಾಸ್ ನಾಟ್ ಇನ್ ಈಕ್ವಿಲಿಬ್ರಿಯಂ. ಯು ಆರ್ ಗೋಯಿಂಗ್ ಟು ಆ್ಯಡ್ ಒನ್ ಮೋರ್ ಫೋರ್ಸ್. ಈ ಫೋರ್ಸ್ನ ಅಪ್ಲೈ ಮಾಡಿದರೆ ಸಮ್ ಪರ್ಟಿಕ್ಯುಲರ್ ಇನ್ಕ್ಲಿನೇಷನ್, ಯು ಕ್ಯಾನ್ ಅಬ್ಸರ್ವ್ ದಟ್. ಸಿ, ಇಟ್ ಹ್ಯಾಸ್ ಕಮ್ ಅಟ್ ದಿ ಸೆಂಟರ್. Now the whole system is in equilibrium. Now we shall check analytically how much magnitude of this particular force you have applied. Idu force ನನಗೆ ಗೊತ್ತಿದೆ, ಇದ್ರ inclination ಎಲ್ಲ ಗೊತ್ತಿದೆ ನನಗೆ. ಕರೆಕ್ಟಾ? ಈ ಫೋರ್ಸ್ ಎಷ್ಟು ಗೊತ್ತಿದೆ, ಇದ್ರ inclination either with respect to 0 or 180 ಅದು ಗೊತ್ತಿದೆ. I'll just give you the problem. ಅದನ್ನು we can find out the value of this particular magnitude of this particular force by using the basic equilibrium condition, which means that you have to resolve each and every force along two mutually perpendicular directions. Correct? Correct? Yes, and then sigma f of x equal to 0 ಮಾಡಿ, sigma f of y is equal to 0 ಮಾಡಿ, you can find out this particular value. ಅಂದರೆ ಎಷ್ಟು ಫೋರ್ಸ್ ನೀವು ಅಪ್ಲೈ ಮಾಡಿದರೆ, this is what you call it as here the equilibrium. You have added this particular force to bring the system to equilibrium. This we call it as a equilibrium. How much magnitude of the force we are going to apply, that we shall check it analytically. ಸರಿನಾ? ಕೂತ್ಕೊಳ್ಳಿ. ಪ್ಲೀಸ್ ಬನ್ನಿ. ಅದು ನಮ್ಮ ಪ್ರಾಬ್ಲಮ್ ಫೋರ್ಸ್ ಆಫ್ 28.23 at an inclination of 7 to vertical. The second force we have applied 210.24 grams at another 4 degree with respect to vertical. And here W4 we have applied 215.08 grams at an inclination of 50 degree with respect to horizontal. And fourth force what we have done is 216.20 at an angle of 22 degree. Istu four forces apply ಮಾಡಿದಾಗ it was not in equilibrium. Okay. Then later what you have done, you applied some particular force at W3. Then the system has been brought to equilibrium. Okay. Find the force W3 for equilibrium. Find the force W3. ಎಷ್ಟು ಅಪ್ಲೈ ಮಾಡಿದ್ರೆ the whole system will be brought to equilibrium. Find the force W3 for equilibrium. ಅವಾಗ ಸೆಂಟ್ರಿ ಬಂತು ನೋಡಿ. ಫಸ್ಟಿಗೆ ಸೆಂಟ್ರಿ ಬಂದಿರಲಿಲ್ಲ, ಆಮೇಲೆ ಫಾರ್ W3 ಸಮ್ ವ್ಯಾಲ್ಯೂ ಲೋಡ್ ಅಪ್ಲೈ ಮಾಡಿದಾಗ ಇಟ್ ಹ್ಯಾಸ್ ಗಾಟ್ ಟು ದ ಸೆಂಟರ್, ವಿಚ್ ಮೀನ್ಸ್ ದಟ್ ಇಟ್ ಈಸ್ ಇನ್ ದ ಸ್ಟೇಟ್ ಆಫ್ ಈಕ್ವಿಲಿಬ್ರಿಯಂ. What is the first thing what you have to do? You resolve each and every force. You resolve each and every force into two mutually perpendicular directions. This is 215.08 cos 50 and this is 215.08 sin 50 are the components of that particular force. Is that right? Then the component of this particular force is, since this is theta, this becomes cos. This becomes adjacent face, that is cos. That is 216.20 cos 32 degrees and this is 216.20 sin 32 degrees are the components. Correct? Then what are the components of this particular force? See, these are the components. Now you can observe that this angle is with respect to vertical. Therefore, this becomes a cosine function. 218.23 cos of 76 degrees and this one is 218.23 sin of 76 degrees. Correct? And this component, that is W2. Once again, you are going to resolve into two components. See, this is the horizontal component and this is the vertical component. Since this angle is theta, this becomes cos. How much? 210.24 cos of 4 degrees and this one is 210.24 sin of 4 degrees. Okay. Now we apply some particular force W3 at this inclination. What is this component? Since this is theta, this becomes cos. Therefore, this is W3 cos 70 and this one is W3 sin 70. Angle ಗೊತ್ತಿದೆ but magnitude ಎಷ್ಟು ಅಪ್ಲೈ ಮಾಡಿದ್ರೆ ನಮಗೆ ಗೊತ್ತಿಲ್ಲ. ಕರೆಕ್ಟಾ? ರೇಡಿಯಲ್ ಡಿಸ್ಟೆನ್ಸ್. What magnitude of force you have applied? Yes, Mundara? We are required to find out the value of W3. If magnitude of the force apply ಮಾಡಿದ್ರೆ the system will be brought to equilibrium. Correct? Yesterday now we have applied that particular force. That we shall check analytically. Is it right? Then we have those two conditions. You know, we have the one of the conditions that sigma f of x must be equal to 0. For equilibrium, for a concurrent force system, how many conditions of equilibrium? Two conditions of equilibrium. Sigma f of x equal to 0 and sigma f of y is equal to 0. Now we shall go for the first condition. Okay, yes, Mandara, what are the components of the sum of all the x components? Taken the one. 215.08 cos 50. Okay, with what sign? Now we shall take the forces to the right as positive and the left we shall take it as negative. This is positive or negative? Positive. Then this is over. Then
216.20 sin.
Then with what sign? Minus 216.20 sin 32 degree. And again this particular force is over. Now we shall go for this particular how much? Minus 218.23 sin 76 degree. Okay, this particular force is over. Then this component minus 210.24 sin 4 degrees. Then this particular component, how much it is? W3 into plus W3 into sin 70. This must be equal to 0 for equilibrium. How the W3 apply ಮಾಡಿದಾಗ equilibrium ಬಂತು. How much force we have applied? That we shall check. Get the value of W3. Get the value of W3. Anybody 215.08 into cos 50 ಎಷ್ಟು? 215.08 into cos 50. ಎಷ್ಟು? 38.25. Then minus 216.2 into sin 32. ಎಷ್ಟು? 4.56. Okay. Then 218.23 into sin 76. 211.74. Okay. Then this one is 210.24 into sine 4 degree minus 14.66. And what is sine 70?
0.939.
0 plus 0.93 times of W3 must be equal to 0. Get the value of W3. Get the value of W3. If you add up money, 138.25 minus of this, minus of this, minus of this, divided by 0.93. Minus 7. See, this is 215 plus, this is minus, this is minus, and this is also minus. Which one then again? Minus
217.96. Sir, plus 217.96. 217.96.
plus
217.96.
217.96
96.
grams. Andre, if you have applied a load of 217, then only it has brought to equilibrium. First to equilibrium irilla. Each load apply madidre, it is brought to equilibrium. Okay? Now you can see this is W3 what you have applied. How much load is applied? Say around 201. Around 201. Is that right? Around how much? I mean, make it 21.
217.96 grams.
201.78. Say 201.78 grams. Apply madidre, that has brought to equilibrium. Now we have applied some particular weight, and now we can observe that particular weight is how much? 200.09 grams. Ali apply madidvi. Avaga matra it is being brought to equilibrium. Correcta? Correcta? Now what is the difference? Just error bantu. Now we got the error. How much is the error? 201.78. Difference of 200.09. It's one today 201.78 actually bego, but we have applied around 200.09. How much is the difference? 1.69.
69.
Okay, this is the difference of load. 69. Okay, 1.69 is the difference of the load what you have applied. What's the percentage error? 1.69 with respect to the initial one is 201.78 into 100 money. 1.69 divided by 201.78 into 100. 0.8%. Now the percentage error, what it from the theoretical value and the experimental value is around 0.8%. Actual value is but there is difference. Why that particular difference is? Now you can observe that these are all the frictionless pulley and thread spring. But in natural practice, here is not purely frictionless pulley. Even purely frictionless pulley, therefore there occurs some value of the friction. Therefore, that particular weight what you apply is different, and hence this particular error. Correct? Now, frictionless pulley, whatever the force you are going to apply at the end, the same has to be transferred to this particular string. But due to the friction that has occurred due to the bar bearings what you have provided, there occurs a certain amount of friction, and hence this deviation. This percentage difference, obviously it is 0.8% with that of the analytical value, hence it is negligibly small. Correct? Now you can observe that first one arc force applied, but we have applied 4 forces, it was not in equilibrium unless center or ring or center point bandirilla. Then you applied some particular force of some magnitude. Then only the particular one has been shifted. It has brought to equilibrium. How much load theoretically you have got? You have to apply 201.78, and experimentally you have seen that you applied a force of 200.09. Almost the percentage error is found to be equal to 0.08%. That is mainly to prove the friction that has occurred well within this particular pulley. Is that right? Now we have demonstrated, okay, experimentally what do you mean by equilibrium? How the equilibrium occurs, okay, for a concurrent force system. Okay, the net resultant must be equal to 0 for equilibrium. Okay, that we have studied. Is that clear? Okay. I done.